Swayam Prabha. Digital India. Educated India.
Welcome to week 3 of our course on Muffler Acoustics. So, in this week, in the next 2.5-3 hours, we are going to talk about different things which will directly introduce us to acoustic filters. So, broadly we will be covering two topics in this week. First is different terminologies that are used to measure sound pressure level, like for example, if sound pressure level is measured in dB or dBA, and intensity, how are they used, how are they related to quantifying the performance of acoustic filters. So, theory part is what we are going to talk about in this week. That is basically without mean flow. So, like I have mentioned, all automobile mufflers invariably have mean flow, because the exhaust gases always flow towards the atmosphere. But before we actually consider the convective effects of mean flow, we will consider a much more simpler case in which the medium is stationary, that is the mean velocity is 0, and we will develop the basic theory of acoustic wave reflection or transmission in the absence of mean flow. So, we will see how these sort of basic elements constitute the muffler analysis, and we are going to elaborate on that. So, let us first begin with some basic terminology that is being used. First is sound pressure level. So, we are following the terminology that P tilde, or the perturbation sound pressure, that is over and above the atmospheric or the ambient pressure. So, both of them consider total pressure. So, this particular thing is always what bothers us. This is what hits our eardrum and produces a sensation of sound. So, this obviously has the unit of Pascal, and our ear, the human ear, can encompass a large range, large magnitude of sound, from very faintest of noise to very incredibly loud noise like a rocket roaring off. So, what we do is basically convert the Pascal to dB. So, we introduce actually a new unit by converting this to logarithm. Sound pressure level is best represented in the logarithmic scale, logarithm to the base 10, where P tilde and with reference with the reference acoustic pressure, which I am going to talk about, and we do it respect to square of this. So, typically here this is the absolute amplitude of the acoustic pressure disturbances in Pascal, and P reference is your 20 mu Pascal, or 20 into 10 to the power minus 6 Pascal, that is 2 into 10 to the power minus 5 Pascal. So, that is the minimum threshold of noise that anyone can hear, that is the healthy human being can hear. So, we always talk in terms of, whenever we talk in terms of with reference level, we are basically trying to basically quantify the noise produced with respect to this, the minimum sound that you can hear, the ratio of that. So, what we do is that this ratio can be a very small number, or basically if it is much less than this thing, then it is obviously negative, but when P tilde is equal to P reference, then it is 1, and if it is very large, it can be incredibly large number. So, basically logarithm is required to properly account for the large variation in the magnitude that is possible in the variation of the sound, in the sound pressure fluctuations. So, we take obviously the square of that. Now, generally this has a unit typically called Bell, named after the scientist Graham Bell. So, we put B, but then usually sound is in the decimal unit, we usually multiply this by 10. So, then this is called decibel. So, this is the expression for sound pressure level in decibel, and this equation can be simplified to your SPL is 20 log to the base 10 of P distinct by P reference. So, here you have this thing, another expression for this thing. So, this is in decibel, and obviously they are different in standard text in acoustics, and you will find human ear is not equally responsive to different frequencies. That is, you tend to perceive 1000 hertz frequencies. You basically, the human ear tends to respond to 1000 hertz frequency in the most in the best possible manner, but low frequencies like less than 100 hertz or 50 hertz, the human ear does not respond to that very well, in the sense that they are hard to perceive. So, basically if you play them at the same level, it is perceived that 100 hertz or 50 hertz sound, very low frequency noise, is relatively less efficiently heard compared to the 1000 hertz. That is why all your ambulances and signals, they are played close to 1000 hertz, if not exactly 1000 hertz. And again, at higher frequencies we tend to hear them alright near about 1000 hertz, but as we go up maybe about 8000, 10,000 hertz, again the same thing happens, that we tend to hear them relatively less efficiently. So, the human ear basically is most responsive near 1000 to 3000 hertz, and beyond 20,000 hertz a perfectly healthy human being cannot hear sounds. Those sounds are called ultrasonics, and frequencies below 20 hertz are called infrasonics. Now, the reason that I have mentioned these things is because we typically, in view of the unequal reception of the human ear to different frequencies, we usually have a thing called A filter, A weighting. So, whatever sound we hear, unmuffled noise, is a customary practice, of course, to account for the different account for the human ear perception and add different weights. So, those are called A weighting. Right now we are not going to go in that, but I just want to mention that here, whenever you account for the different frequencies that human ear listens to, you typically end up with a thing called A weighting, and such a thing is called A weighted noise. But right now we will just focus on the dB, decibel level, and not dBA. Of course, there are other scales also, dBc or other ones, but that is what it is. Now, there are other things also, just like you have SPL, you also have intensity level. So, before talking about intensity level, let us formally quantify what is intensity. So, now let us talk about definition of acoustic intensity. So, here you are, acoustic intensity. Acoustic intensity. Now, basically spherical waves, basically the waves that propagate in 3-dimensional space, they tend to expand out. So, the same acoustic power, that is, imagine a sphere like this, and if it is expanding out, so the area of the sphere becomes more. So, the same acoustic power is spread over a sphere of a larger surface area. So, if you have a look at this figure, if you consider a small slice of the sphere, so this is, let us say, the cross section area S1, and this is your S2. So, basically what we do, if we go by the basic principle, intensity is nothing but basically power by, let us denote this by W divided by area. So, this is power of work done, that is your basically force into velocity divided by area. So, this is pressure into the A into V, this is A. So, here you are P into V or U, whatever you want to call. So, the instantaneous intensity then is your nothing but acoustic pressure, instantaneous acoustic pressure into the normal velocity, that is the velocity of the particle is normal to the surface. In this case, this orangish line is normal to the surface. So, and here you have basically, when I talk about a bar, It means one needs to take the product of this thing and take the time average of the product. So, basically the average intensity for one cycle or a certain time t average would become your 0 to t AVG average into P u dt, where this is acoustic pressure and this is the normal velocity to the surface. So, we do it over a certain time. Now, for non-periodic waves, that is for random signal t average, this tends to infinity, but for most signals emitted by machines or other equipments, they have some sort of periodicity. So, basically we can talk about a certain period. So, that is t average is finite. There are special formulas for intensity that are developed for two somewhat overlapping class of problems. One is progressive wave or of arbitrary waveform in lossless fluids, and other is time harmonic waves, which are need not be necessarily progressive, and they can be in arbitrary fluids, but we will talk about air and we will talk about particularly about lossless fluids only. So, this is the expression that we will use, and here this thing can be further simplified if we have a free space. So, if you recall our discussions in the first and the second week, we saw the P by U or UN, if you want to say, is rho naught C naught, that is a characteristic impedance of air. So, UN then can be replaced by this thing. So, I would become 1 by T average and your 0 to T average and P square by rho naught C naught dt, right. So, what I can do is that take out 1 by rho naught C naught common, it is constant, and 1 by T average and 0 to T average and P magnitude square dt. So, I will become P RMS square by rho naught C naught, where P RMS is root over 1 by T average and 0 to T average square. So, this is something like this. This is one expression for the RMS acoustic pressure. So, what one needs to do is that if we know the time series of variation, suppose if you have a signal, the acoustic pressure signal, and you using a microphones are used for measuring sound. So, if you have certain variation like this, so once we know some time series, then we can write a algorithm, write a simple MATLAB code for example, or whatever programming language you use to figure out the RMS value, and this can be used directly in the equation 3 P RMS to give us the sound pressure level. Now, talking about the intensity level, how do we go about making use of the intensity to that? So, just like we have defined sound pressure level, intensity level IL is defined as 10 to the power log to the base 10 I by I reference, where I, like I said, is given by P RMS square by rho naught C naught, and I reference is just like we have P reference as 20 mu Pascal, I reference is 10 to the power minus 12 watt by meter square. So, for now we will just put this as I reference and simplify this expression. So, intensity level then is your 10 log P square RMS square by rho naught C naught times I reference. So, this becomes log of P RMS divide this by P reference square, and this entire thing is square, and you have your P reference square by rho naught C naught times I reference. So, let us go to the another slide. Intensity level then is your 10 log to the base 10 of P RMS square plus 10 times log 10 P reference square divided by rho naught C naught times I reference. So, if we were to do the maths, we will see this is nothing but 20 log little bit of algebra, and would reveal that this is nothing but this plus 10 times log 10, and we just need to put the values now. 414 or something like that, and this is 10 to the power minus 12. This would become SPL in dB, of course, and minus this entire thing turns out to be minus 0.16, of course, dB. Intensity level is sound pressure level minus 0.16 dB. So, basically for all practical purposes, intensity level is nearly equal to the sound pressure level. That is what we take. If they are numerically the same, 0.16 would not make much difference. Now, there is yet another thing called sound power level. Not to be confused with SPL, this is called PWL, and lot of machines that you buy, for example, air conditioners, refrigerators and other electrical appliances used in household or even in industrial setup, the manufacturer often has to specify the acoustic power that is radiated by the machine in dB or dBA. So, reference it again like intensity level or sound pressure level, this also has a certain reference, and that is 10 to the power minus 12 watt. So, how do we compute the sound power level? This is given by 10 log to the base 10 of W by W reference, which I have just mentioned here. Now, basically sound pressure level is a measure of the total acoustic energy per unit time emitted by the source. It cannot be converted to sound pressure level until additional information is provided, especially like the directionality of the sound, distance from the source and so on. But nevertheless, a useful expression for the sound pressure radiated, which will be particularly useful for evaluating the performance of mufflers, is basically intensity into S. So, suppose if you have a duct and you have some progressive waves going in certain direction. So, intensity into surface area. So, suppose this S is the cross section area. So, intensity into surface area is the acoustic power. So, we just saw a while back that intensity is nothing but P RMS square divided by rho naught C naught, and if you multiply this by S, we are going to get the acoustic power. So, we will see in due course that acoustic pressure as a function of x is A into the e to the power minus j k naught x. We are neglecting the waves that are coming from the opposite direction. We are considering only waves that go like this in this direction and not allowing waves to come. So, it is a progressive wave. Now, the RMS thing would be A by root 2. So, typically we would get things like this. So, we will eventually see the acoustic power carried by a progressive wave would be 2 by rho naught C naught times S. And we will see how these definitions are useful to these expressions are useful for evaluating the performance of mufflers. There are a few derivations, of course, that I thought it is little important to talk about now. So, generalized expression for impedance is P by U or UN, whatever you are comfortable with, normalized impedance, and this is real part of Z plus J times imaginary part of Z. You can probably write this as Z E J theta, where theta is the phase angle between P and U. So, intensity then becomes omega by 2 pi, and if you were talking about a period. So, how did this omega by 2 pi thing came here? Because time period is nothing but 2 pi times omega, right. F into t is equal to 1. So, and if you multiply both sides by 2 pi, you are going to get this thing, which implies omega into t is equal to 2 pi, which means time period is 2 pi by omega. Well, so in the expressions that we have at our disposal, basically these ones, T average would become T, this would be equal to 2 pi by omega, or omega is the angular frequency in hertz. So, now let us write down quickly what it means for us. It means pressure can be thought of, pressure is nothing but impedance times U. So, it is we talked about real part of this. So, real part of pressure into real part of velocity into dt, because these signals can be put in the complex form. So, this again would become 2 pi by omega. So, we need to go to the next slide and formally define this thing. I is omega by 2 pi, and once you simplify it further, what are we going to get? 2 pi by omega z u square, because here real part you can think of this as u amplitude, u times magnitude of the amplitude, and this is magnitude of the impedance times cos omega t plus beta plus theta into cos of omega t plus beta, where beta is the general phase of the signal. So, once we do the algebra, work out these particular nasty looking expressions, and what are we going to get? So, most likely after a lot of simplifications, we probably would get this as half of z times cos theta times u square, or and now that we recognize that z cos theta is nothing but real part of z, and magnitude of u square, this is nothing but u RMS square, we obtain I equals real part of z, because this is something that we are taking together and this thing we are clubbing it here to get u RMS square. So, clearly the physical significance is that if we keep the material, the propagation material constant like air, and if we have increased particle velocity, that is the oscillations are going on at with a larger amplitude, larger u RMS, then obviously the acoustic intensity will increase many a fold, and this will have consequences on the hearing that we do. So, yet another form, this is similar to your electrical circuits. We will probably talk about that in a much greater detail, but for now let me present to you yet another expression for the intensity, which is P RMS square divided by Z times cos theta. How did we end up getting this? So, if we recall this one, U also can be written as P by Z, right. So, we can put these expressions here to simplify further. So, once we do that, we can get real part of pressure into real part of pressure, that is P RMS square, and you will get in the denominator Z cos theta. And if you simplify this thing further, we are probably going to end up with this expression, and this can be further written as half of magnitude of P magnitude of U into cos theta, where theta is the angle between the acoustic pressure and the particle velocity. So, if they are in phase, then cos theta is 1. So, you just have half of magnitude of P and U, that is basically in the far field acoustic pressure and acoustic velocity are in phase. You typically end up with things like this thing, where rho naught C naught is sort of absorbed in this constant P. Then you can keep on presenting different expressions for this, but in context of duct work or propagation through one dimensional ducts, we typically will see that we will end up with a progressive wave of amplitude A. The acoustic power that is carried by wave in this direction is given by A mod of A square, that is amplitude A square, divided by 2 by rho naught C naught into S. Similarly, the waves that propagate in the opposite direction, their magnitude is B, and the acoustic power carried by them in this direction is B square by 2 rho naught C naught S. So, we will worry about all those things in the next lecture. So, for now we will stop here and talk about acoustic filters, that is some fundamental elements used in mufflers in the next lectures. Thanks.